Hello and welcome to the course Design Borefields with Confidence. This is the third chapter of the third part and we will be talking about variable flow rates here. Now, the third part of this course was all about how newer state-of-the-art models in GHCTool can help you design better borefields. And last chapter we already talked about variable fluid properties, where we will not be taking anymore one constant viscosity and so forth for the whole simulation period, but we will be actually calculating it at every hour or every month. We will update the Reynolds number as well as the borehole resistance. And we showed that that can have a very, very big effect, especially when you're dealing with quite a lot of cooling demand. So it's a must-have basically for designing accurate borefields anno 2026. Now today we will be looking at a different aspect, namely variable flow rates. Now to understand this, we have to look at a very important equation in the whole of heat transfer, basically. And it's given here on the slide. And it's the relationship between power on the one hand and the flow rate, the heat capacity, and the temperature difference between in and outlet on the other. Now, one thing we need to do first is, this is not an equation of constants, because your power can change over time, and so can your flow rate and your temperature difference. So let's make this time dependent. Now the next thing I want to mention before we dive a little bit into the flow rate is this heat capacity of the fluid. It's a fluid property and we talked about it in the last chapter. It changes with temperature. Now for every temperature at every time of the simulation period, it's basically a given. Once we decide which heat transfer fluid and which percentage of it we want to use, we have no influence on what the specific heat capacity will be at every hour. It's a given. So let's not talk about that for this moment, because it's not something we can change at this time of the design as a designer. So let's assume it's constant. And then we have a relationship between, on the one hand, variable power, changing power, heating, cooling, and so forth. And on the other hand, a combination of either a variable flow rate or a variable temperature difference. And this gives us two different viewpoints. And the one is the traditional one where we say, okay, let's use a constant flow rate. So this means that our m dot, our flow rate, is now a constant. And when our power changes, also our temperature difference across the inlet and the outlet of the borehole will change. Now the other newer and, as I will show later, accurater assumption is using constant temperature difference. Where we say, no, okay, let's work with a fixed difference between the in and the outlet, and let's change the flow rate such that we have the required power at every instance. Now this is a newer approach. Now just to illustrate, the constant flow rate is a historical assumption which was basically rooted in the fact that pumps were on off, and they were either at the maximum flow rates or they were not working at all. There were no frequency control pumps back in the days. And also there were no modulating heat pumps. So the power, when it was on, it was always the same, and our flow rate was always the same. And this worked rather well. But now, with modulating heat pumps, and we will talk more about that in the next chapter, our power, our demand from our ground, is no longer constant. It changes from hour to hour, and also our flow rate will change. So using a constant flow rate is quite a big assumption and not quite an accurate one when working with frequency controlled pumps. And the second issue is that now that buildings have both heating and cooling demand in most parts of the year or the world, the thing is, do they have the same flow rate? When we have way more heating or way more cooling than the other mode, will they have the same flow rate? Probably not. So also here, constant flow rate can actually have even some danger for undersizing your system, as we will show later in this video. So when we're working with a constant temperature difference, it's basically the same as saying we're working with a variable flow rate. So what we do here is basically bring our simulation in line with reality. And when you have a frequency controlled pump, the most common way to control the flow of your system is actually to work with a constant temperature difference across your heat exchanger or your heat pump. And typically your heat pump, it works with a temperature difference of 3 to 5 degrees, depending on your model. And it's such that the efficiency of your heat pump is actually optimized. And what happens, especially if you have a modulating heat pump, when the power it should deliver to the building is lower, also your flow rate will change such that a constant temperature difference is kept. So that's why working with a constant temperature difference, a variable flow rate in GHG tool is way more accurate. Another advantage is that now we have a different flow rate for both heating and cooling. And it does not longer need to be the same. So we can also make quite a lot of improvement there. And the last thing I just want to mention is that we also have something which is a minimum flow percentage. A frequency different pump, it can work somewhere between 30 and 100% of its rated maximum power. It cannot go all the way down to 0. And this has some practical limits, as I said now, that's the whole working range, but also some theoretical ones which are written in the textbook if you're interested. So we're also working with a minimum flow percentage somewhere between 10 and 30%. Now to illustrate the power of using this variable flow rate, let us look at a typical example where this is important, namely an office building. And as you can see here, our peak cooling, it's 370, I believe. It's way higher than our 200 for heating. So of course, our flow rate during this cooling demand will also be significantly larger than during our heating demand. So that's the one thing. And the second one is, you can see that there is quite a lot of variation. And in cooling, you can see that very clearly, that there are periods of low cooling with 100 kilowatts and periods of 200 and 300 and more kilowatts of cooling. But also you see these white lines, which are basically the weekends. In the weekends, an office building is not used, and there is no heating and cooling demand. It's just a very small demand to keep the building basically at the minimum threshold. So there's also quite a lot of variation in required power. And what we did, just to illustrate, is we took this profile, we simulated a borefield with it using both a constant flow rate and a variable flow rate. And we made it such that our constant flow rate, it was actually set to the maximum flow rate we will have during this peak of 370 kilowatts in cooling to basically match our design. And so our maximum flow rate is the same in both simulations. And the results is given here. So indeed in summer, you can see we reach a 25 degrees limit here, and our constant flow and our variable flow, they are the same. And because at that instance, the flow rate is also the same. It's only when we move away to periods with lower peak powers that we can see some difference between the constant and the variable flow. And especially when we go to winter, when there is quite a lot of heating, we see that our constant flow rate, if we look at the first months, fluctuates between 10 and let's say 6.5, something like that. But when we go to a variable flow rate, the amplitude is way bigger. It goes from 10 to 3 degrees something. So we are underestimating the real temperatures when we're using constant flow. Because during this heating, our peak power is way lower, powers are lower, so also our flow rate is lower. And as you can see, our borehole resistance is no longer turbulent in this case. Now, before diving into that, I want to draw your attention to the constant flow rate case here. It's not a line, it's basically there is some noise on it, let's say. And that's due to basically what we talked about last time. If we have variable fluid properties, also our Reynolds number will change depending on the temperature and the time of the year. Now, last time we had cases where this result was very significant and we moved in and out of turbulence when we switched from heating to cooling. This is not the case here. So with our maximum flow rate and designed for cooling, we were turbulent the whole year around. So that's why it's more or less constant here. However, the difference between our switching from laminar to turbulent flow, it's now because our flow rate is no longer constant. And you can clearly see that we have a very good effective borehole resistance during specific times in summer, where you can actually see both the constant flow and the variable flow rate, the Reynolds number, the borehole resistance related to that, they overlap. It's the peak powers where also the flow rates are constant. However, moving towards heating or even periods with lower cooling, our flow rate will be lower, we will not get into turbulence anymore, and we fall back with a lower laminar effective borehole thermal resistance. And this is very significant, and it's very significant in most cases, actually. And that's why working with a constant flow rate, it's often an overestimation of what your effective borehole resistance will be. And it can both lead to undersizings, unexpected undersizings, but also to wrong insights. And to illustrate that, we jump into GHE2 and talk again about the residential profile, the residential building we simulated last time. So in GHE2 Cloud, I created two scenarios, basically the same ones, the same residential building as before, with a monthly and an hourly load profile. The only thing I changed is the borehole resistance now. I changed it from a W tube to now working with single one, 25% of monoethylene glycol, just to give you a little bit a different viewpoint. And our flow rate is constant at just short of 7 liters per second. Now, the 7 liters per second, it will be clear where it comes from when we switch to constant temperature difference simulation. It's basically the maximum flow rate we will have during our peak cooling. Now, to recap, our thermal demands, again, if you want to follow along, the report of the simulation is actually also in the textbook, so you can download it there and recreate it yourself. We have a slightly higher demand for cooling in this case, 77 kilowatts, only 62 kilowatts heating, but the yearly heating demand is actually way bigger than the yearly cooling demand. So if we simulate this, we have our numerical results, and you can see we're transient and turbulent in both extraction and injection, with our just short of 7 liters per second, good effective borehole resistance, and we have a very significant imbalance, but we stay beautifully within the limits. We are above the 2 degrees with 2.6 and below the 17 with 16.4. So actually it's even a little bit oversized, one can argue, but it's actually designed accurately. I will come back to the hydraulic design in the next part, but just to illustrate, we have here a flow rate of 6.93 liters per second in both injection and extraction. Now let's make the same simulation, but now with a variable flow rate. So let's duplicate it and call it a variable flow. And the only thing we need to change for that is we go back to the borehole resistance step, scroll down, and say, okay, let's work with a constant temperature difference. And let's work with a temperature difference of 3 degrees Celsius in this case. And let's calculate it now. So now it will, at every month, we take the peak power, we calculate the flow rate, and we end up with this result. And what you can see already without looking at the profile is we're now at 1.5 degrees Celsius. So now we're basically not sized correctly if we compare that to our constant flow rate. So working with a variable flow rate in this case actually gives us a worse design. And why is that? It's because we're now no longer turbulent during extraction. Now our flow rate, if we scroll down, is now only 4.28 liters per second. Because yeah, our peak power is only 62 liters per second and not 77, giving us a lower flow rate and also, hence, a lower Reynolds number and borehole resistance. You can see that our maximum flow rate is still just short of 7 liters per second. It does not change there. But for heating, for the extraction demand, we actually overestimated the flow rate. Meaning that we overestimated the borehole resistance. It's no longer around 14, it's now 24, which is way worse. And now we're actually not sizing this borefield accurately. So where we would say before, well, perhaps we can do with one borehole less, here we would need to argue, okay, perhaps we need another borehole to stay above this 2 degree limit. So working with a constant flow rate when you have different heating and cooling demands can actually be misleading. And the same story holds when we're doing this simulation hourly, of course. So if we do it hourly, we have different temperatures. Now we are quite close to the minimum limit, 2.09. Looking from an hourly perspective, we would argue, okay, this borefield is sized correctly, 2.09 or 2 degrees. It's really close together. So let's duplicate this as well and also make it a variable flow rate. So variable flow. Let us go to the borehole resistance tab, scroll down and say, okay, let's now calculate with 3 degrees and 3 degrees. Of course, for your own simulation, you can also play around and see what happens if we change it to a different temperature difference, of course. So now we have the results, and we already clearly can see that, as was the case with the monthly profile, we are now way below our 2 degrees threshold. So surely this borefield is not sized accurately, again, because in extraction we are laminar. It's no longer turbulent flow there. And if we zoom in, let me do that first with the constant flow rates. On, for example, the last year in winter. So you can see that our borehole wall temperature and fluid temperature, they're actually quite good together. And that's because of borehole resistance, as we discussed over on the last part. It's good. So the fluid and the borehole wall temperature are close together. However, if we do that with the variable flow, you can already see it at this scale, but if we zoom in, it's clear that they are way further apart. So the heat transfer due to the laminar flow rate is now not that good. And this is an insight, this is something that we miss completely when we're designing with a constant flow rate. Now another thing one might think about is that we risk having wrong insights with the maximum temperature. So if we now go back to the constant flow rate and let us zoom in at the first year in summer. Again, we know that it's not critical at the moment and we stay away from the 17 degrees limit, but let's assume for a second that it was at 15 degrees. One would argue here, okay, when do we cross this 15 degrees? It's like 5 hours in the year, this 15 degrees, so it would not be that big of an issue. But of course, this is a constant flow rate, and the periods when we have not 77 kilowatts of cooling demand, but we only have 70, for example, chances are we're not that turbulent anymore. And if we switch to a variable flow and I would zoom in that same period, we would see that we are way often very close to this 15 degrees. We cross it perhaps only once, but also here we're now crossing this 15 degrees limit because probably there, we're not that turbulent anymore. We're already in the transient, perhaps even towards the laminar flow rate due to the lower circulation. And that's a very important thing to see or to understand, that if you're using a constant flow rate and you're making these estimates or these decisions, well, okay, we're not crossing our limit quite often, or we're not often close to it. If you move to variable flow rates, chances are these insights are different and you're actually closer or way often closer to this limit than you would have thought when working with a constant flow rate. So these were two insights I wanted to share with you, that working with a constant flow rate cannot only show you a potential undersizing of your borefield when you're different flow rate in heating and cooling, for example, but also it can give you wrong insights or misleading insights when looking at the hourly profile in particular. So for your own case, also to avoid making any mistakes, basically, it's just easier to work with variable flow rates. Your insights will be better and your results will be more accurate. And in GHCtool, it's really easy to do so. So this was what I wanted to say for this chapter. The last major improvement we made with GHCtool for the whole designs industry is basically stepping away from using constant efficiencies towards using variable efficiencies, modulating heat pumps implemented in GHG2. It's something we are going to discuss next chapter.